Let's analyze our case number 3, where we explore how to guide core replacement using 3D structure-based information. Here, we look at a scaffold hopping as a strategy, taking an existing molecule and replacing its core. We start from structural information, a resolved protein ligand complex that gives us insight into which part of the molecules are making critical interactions and where there's room to grow. In this case, the reference compound is a non-PIN1 inhibitor. We've identified a region of the molecule that we want to change and introduce novelty. Macchia's fragment linking generator takes this structural context and proposes new cores, replacing the central scaffold while preserving the key interactions. Once we've identified a region of the molecule for core replacement, Macchia allowed us to fine-tune the design using chemical constraints, making the exploration more controlled and meaningful. Here we set exit vector number 1 and 2, essentially defining where Macchia should connect the two fragments, introducing new core design. From there, we can apply filters such as abstractor constraints like paints and tucks, descriptor-based filters like molecular weight. Then Macchia will predict which building block and reactions are the best to generate the final molecule from the two starting fragments. Macchia is not working alone. SPIA plays a critical role in ensuring that the molecules proposed are actually synthetically accessible. SPIA is a chemistry-driven. It understands reactions feasibility, cost, and route complexity. Here's the joint output. Macchia proposes novel scaffolds based on design constraints. SPIA traces back viable synthetic routes. Together, they prioritize compounds that are both effective and feasible. To guide core replacement effectively, we don't just rely on structural data. We also need to be smart about how we define the problem for the generator. This is where SPIA comes in. By analyzing retrosynthetic routes, SPIA helps identify exit vectors that are not just chemically relevant, but also synthetically viable. These become the anchor points we fed into Macchia to drive scaffold hopping. In this example, exit vector 1 and 2 were chosen based on SPIA retrosynthesis, ensuring we focus on regions where new chemistry can realistically be made. So now let's walk through how we actually set up and run this core replacement experiment using Macchia. First, the 3D structure-based settings we use here are the same ones we apply in case 1. If you need a refresher on that setup, you can go back and revisit case 1. We begin directly on Macchia's generator page. This is where we define our two initial fragments, which can be informed by SPIA's retrosynthetic analysis. We also set the exit vectors, the boronic acid, and the secondary amine to define the reactive centers where Macchia will connect the fragments and propose new core replacements. We then introduce certain product constraints. In this case, a maximum molecular weight of 500, a minimum of QED of 0.3, and also a custom list of paint stocks that we want to completely avoid. Then we apply the 3D scoring setups. These steps tells Macchia which reward functions to use to prioritize the generated molecules. Again, if you need a refresher on the setup, you can go back and revisit case 1. Finally, we visualize the results. All generated molecules retain the original two fragments, but between them, Macchia has introduced diversity in the form of new core. If we dive into the details, we can see the predictive building block that Macchia chose to connect the two fragments, and also we can see different scores such as Vina score, contact score, and the retrosynthesis one, which will tell you how synthesizable the final molecule is. You can also visualize the final molecule docked inside of the protein pockets, compare it to your reference ligand, and also visualize all the new interactions that Macchia created.